In this short video, what we're going to do is recap our understanding of rates of reaction from the first year of the course. So in the first year we looked at rate of reaction as the change in concentration of a substance in a given time. So we might have looked at the change of concentration of a reactant decreasing or a product increasing over a set amount of time. So if we take that apart, we can figure out what the units are. So we know that the units of concentration are moles per decimetre cubed, and we're looking at how that changes over time, and the SI unit of time is the second. If we put all that together, we'll get moles per decimetre cubed per second. So if we think about that, what we would be looking at is if we were measuring concentration against time, then we might be looking at, if it was a reactant, at that falling over time, or if it was a product, at that increasing over time. And then this rate would be measured if we're looking at the change in something on the y-axis over the change in something on the x-axis. We'd be looking at what we would call the gradient by finding the tangent and taking the gradient. Then we'd be getting a measure of the rate. So there we go. If we want to find the rate from a concentration time graph, we would draw a tangent and measure its gradient. Now if we wanted to find it at time equals 0, that's kind of what I've drawn with the red triangle. We measure that tangent at time equals 0, but we could find the rate at all sorts of different times, and we'll find that the rate is changing over time, and that's to do with the frequency of collisions, which is where our collision theory comes in. So remember from last year that for a reaction to occur, collisions have to take place with sufficient energy, and this sufficient energy is called the activation energy. So the activation energy is the minimum energy required to start a reaction by the breaking of bonds. You'll take each of the factors that can affect rate of reaction and see if you can remember why they affect it. So pause the video and see if you can write an explanation about how changing concentration will affect the rate. So there we go. We can remember that when the concentration of reactant increases, what we're actually talking about is that there are more particles per unit volume. That's what we mean by an increase in concentration. We've got more moles per decimetre cubed, more particles per unit volume, so we've got more successful collisions per unit time. We've got an increase in the frequency of successful collisions, and therefore rate increases. So pause the video again and see if you can write why pressure affects rate. So here we go. When the pressure of a gas increases, there are again more particles per unit volume because you've squashed that gas into a smaller space, so more successful collisions per unit time. Again, rate increases. So very much the same reason there, but just about gas pressure. Okay, so pause the video again and see if you can write about surface area. So here we go. Just be a little bit careful on this one. There aren't more particles per unit volume. There's the exact same number of particles now, but what we do have is more solid particles exposed with an increase in surface area, so there are more successful collisions per unit time. A measure of rate is a measure of those collisions, the frequency of those successful collisions. Now, temperature and catalyst, you just got to bear in mind the explanation is a little bit different and takes into account activation energy. So pause the video and see if you can write about temperature. So here you just need to be careful and not fall into the trap of saying because they're moving more, there are more collisions for that reason. But that is very small impact in comparison to more particles with energy greater than or equal to the activation energy. So that when they collide, many more of the collisions are successful. So many more particles have energy greater than the activation energy, and many more collisions are successful, and therefore the rate increases. So pause the video one final time and see if you can explain catalyst. And here we go for the final one. A catalyst is going to provide an alternate route of lower activation energy. So more particles have energy greater than the activation energy, and we've got more successful collisions per unit time. Now remember that these last two here can be explained using the Maxwell-Boltzmann distribution curves. And if you've forgotten what those are, it might be worth going back to your A1 pack now and having a look at the Maxwell-Boltzmann distribution curves and seeing how you can explain temperature and catalyst using those. So that's the end of this little short video recapping last year's work.